Okay, so up until this point, all the forces we've been talking about have been constant. So now we're going to talk about what happens when that force is no longer constant. Easy way to recognize this is that in a problem, they will give you a function for the force. That's just the easy way to look at it. So all the prior forces we spoke assumed that a force is constant. Now, if the strength of the direction of the force, not of the right, of the force is not constant, the angle between the force and the displacement is also not constant. Okay. Now, what happens is the path taken by the object is no longer a straight line. Right. So all these prior examples, right, the path taken by the object would be a straight line. And now what happens is once you start varying the force, okay, the path will no longer be a straight line. And so to calculate this, right, you're going to have to do the integral, okay, to find how much work is done. So just a couple of examples here, right? The first is spring force. And we're going to do a lot of work in this area. And then the other example would be a pendulum. Okay. Now, if a varying force is represented by a force versus position graph, okay, the area is what represents the work done, right? So in AP Physics 1, a lot of it will look like this, right? So you have a constant force traveling a specific distance, and your area is the work done, right? So this here would be the work done. Now, in Physics C, right, we're going to get things like this, right? We're not going to get nice functions, right, where we're going to have to find the area under this function, right? So it'd be like xi, xf, okay? Where again, under here is our work, okay? But we have to do, it's not as simple as just simply like finding the area of a rectangle. Here we're going to have to do the area of this function, okay? So when you're given a force that is a function of position s or x, we'll call it x, not s. So we'll change all these s's to x, okay? The work the work done by this force when an object is displaced from xi to xf is work equals the integral from xi to xf of f of x dx, right? And remember, that dx translates back to delta x, right? And so those are the little increments, right, that we add up over time, because remember, integrals are simply the sum, right? It's called a Riemann sum of all those little delta x's. Okay, so here's an example where this happens. Now, like I said, we're going to do a lot with springs, but we could do it really for any force. And you'll see here that we have a 1,500 kilogram car being towed starting from rest. The tension in the two ropes, the tension in the two ropes as the car travels from 0 to 200 meters is given by the function t of x equals 5,000 minus 25x. What is the car's speed after being pulled the 200 meters? So again, this question is going to come back to delta k equals w, right? So what we need to first determine is w, so that we can use this relationship, okay? And so the work done will be the integral from 0 to 200, right, of our f of x, which is 5,000 minus 25x dx, right? And so if we take the integral here, remember, if it's a constant, it becomes a line. And if it's a line, it becomes a quadratic, right? becomes 1/2 x squared. And we're going to evaluate this from 0 to 200. Well, the good thing is all we really have to do is plug in 200 here because, right, if I plug in 0 for those two parts of our function here, it just becomes 0. So we're going to do 5,000 times 200 minus 25 over 2 times 200 squared. And so the amount of work done in doing this is 9.6 times 10 to the 5th joules. Okay, now we come over to our work energy theorem side. And so we're going to do delta K equals W because we're looking for the speed. If I do a little solving, in fact, if you go back to the video on work as a dot product, you'll see that it's just going to be this equation right here, right? The only difference is for this problem, our initial velocity is 0. So it's just going to be the square root of 2W over m. And so V is going to be the square root of 2 times 9.6 times 10 to the 5th joules divided by our mass, which is 1,500. Okay, and so after traveling and starting from rest and traveling these 200 meters, we're going to have a velocity of 35.8 or a speed of 35.8 meters per second. Okay, so again, just a reminder, all right, anytime your function is given or your force is given as a function with respect to x, you're going to have to use this equation, right? You're going to have to find the work by doing the integral. Now, the next example, what we're going to do, or the next section, is we're going to look at specifically springs.